Work and conservation of energy, focusing on the law of conservation of energy, which is probably one of the biggest guiding principles for this semester going forward. So the law of conservation of energy. Energy cannot be created or destroyed. It can only be transformed from one form to another. So here's a bunch of illustrations. Example number 5, continuing from yesterday's lecture. But we have a baseball being thrown from the outfield towards home plate. Let me pause and draw the diagram. So here we have the diagram, and when it says the ball at the apex of the path, apex means the top spot, like the top part of the parabola, if this were a complete parabola. At that spot, as we learned from projectile motion a couple of units ago, the ball is only traveling horizontally, in this case, still pretty fast, 32 meters per second, like over 60 miles per hour. So this outfielder gave the ball a pretty good heave. At that top spot, the ball has potential energy, gravitational potential energy, and kinetic energy. Now, what we'll say, for abbreviation's sake, the ball at that top spot has a TME. TME stands for total mechanical energy. Total mechanical energy. I'm going to refer to TME quite a bit in these next few problems. So at that spot, at the apex, the TME is equal to the kinetic energy of the ball plus the GPE of the ball. So we can calculate that all out here. I'll go backwards here. The TME is going to be the kinetic energy, which is 1/2 mv squared plus mgh. So the total mechanical energy of the ball at that top spot is 1/2 times the mass, which is 0.96 kilograms, times the velocity at that spot squared, 32 meters per second squared, plus the mass, which is 0.96, times g, I'm going to round that off to 10, times the height that it gained, the 5.7 meters from the ground, that the outfielder picked it up from the ground. So if we do the calculation here, we get TME equals 492 joules for the kinetic energy, plus 54 joules of GPE. I'm leaving off the units for the time being until I add these. The TME is 546. That's a 546 joules of energy. Now, since the ball was laying on the ground when the outfielder picked it up, that is also the work that the outfielder did, because what the outfielder did is transferred chemical energy from his body to the ball. So the work done is 546 joules. That was a transfer of energy from the fielder's body into the ball during this process. All right, the second example of applying the law of conservation of energy. We cannot create or destroy energy. This person, once again, and this is my little diagram here, it's supposed to be a pole vaulter. That long black, I'll make it blue. That's supposed to be the pole that they're running with. And then we have the red high bar that they're going to jump over. Anyway, this person's going to do work. They're going to speed up and gain some kinetic energy, transferring chemical energy out of their body into kinetic energy. So what we want to do here is figure out the kinetic energy of the pole vaulter, assuming their top speed is 9 meters per second. And if we do that, the kinetic energy of the pole vaulter before they vault themselves over the high bar is 1/2 the mass of the pole vaulter here, which is 58 kilograms, times her top speed of 9 squared. So her maximum kinetic energy turns out to be 2,350 joules, rounded off to 3 sig figs, that they can use to transfer into GPE. So that's what we're going to do here. This person, as they're running along, has that kinetic energy. It's going to transfer into potential energy we're going to assume that when they get to the very top, as they're just getting over that high bar, they essentially have zero velocity. They're pretty much going straight up, almost, and then straight down, ignoring any little sideways motion. So what's going to happen is that kinetic energy is going to transfer into GPE, which will be their mgh. Well, so we just plug in the 2,350 as the GPE that they're going to gain as they lose the kinetic energy, equals the mass, which is 58, times 10 for the acceleration due to gravity, times the height gain. And it turns out here that that comes out to be 4.1 meters. Now, essentially that's the answer. However, we need to tweak this a little bit. And by the way, 4.1 meters is roughly 13 feet, which actually is quite low. Well, it's not that low. It's probably pretty good for a high school pole vaulter, but for Olympic pole vaulters, it's not very high. And here's the one little tweak here. It turns out that 4.1 meters is technically the delta H. The gain in height that the pole vaulter gets is the 4.1 meters. And here's something we'll talk more about later on, but essentially the center of mass of a pole vaulter, or a person in general, which is what we really want to look at here, is around your belly button. And if I go to the diagram, somewhere, I don't know, around belly button, that's not quite the belly button, but is about 3 feet off the ground, about 1 meter off the ground. It's already about 1 meter off the ground. So in other words, in this particular case, if there is a gain in height of 4.1 meters from where your center of mass was, 1 meter off the ground, essentially the pole vaulter is going to possibly be able to make it to a 5.1, or about 5 meters off the ground, which is more like 15, 16 feet, more in line with what an Olympic pole vaulter would do. You don't need to put down the 5.1 meters here. The 4.1 would have been fine, but I'm just showing you a little bit more of an extended idea here. Third example for the conservation of energy. So here we have essentially a roller coaster. We're ignoring friction here. We have a car on the top of a hill, 40 meters tall. Now it's over 100 feet. It's quite high up there. I'm going to call the initial spot, and the car is already moving, and it's at the very top spot. But I'm going to call this top spot, and we're going to look at, once again, the center of gravity of the center of mass or center of gravity of the car. We're going to call that point A. And the car is going to come down the hill, and it's going to get to the bottom over here with a higher speed, like a roller coaster would get. We're going to call this spot down here point B, the low spot. Then it's going to coast back up to the top of the other hill, which is not quite as high as the first hill. I'm going to call that point C. So now I'll apply the law of conservation of energy at point A. I'll go back to point A over here. And what's going to happen, what's happening is that the total mechanical energy at point A is equal to its kinetic energy, that says KE at point A, plus the GPE at point A. The total mechanical energy at A is 1/2 its mass. Now we're not given the mass. That's a little bit concerning. I'm just going to put an M there for mass right now, times the velocity. I do have the velocity, 10 meters per second squared, plus the GPE at A, which is the mass, once again we don't know it, times 10 meters per second squared, the acceleration due to gravity. The 10 over here for the kinetic energy, which is the 10 meters per second. This is 10 meters per second squared for gravity's acceleration, times the height, which is 40 meters. All right. Now the M in that equation there is not meters, it's mass. The TME will have to be done symbolically here. 1/2 times M times 10 squared, 100. It's 50M plus 400M gives me a TME at point A of 450 M, where M is the mass, not meters. And the units would be joules. Let me ignore the units for a few minutes here. Now at point B, and let me go back up over here. This is actually, I'm now starting to answer question A, or part A of this problem. The TME at point B is just kinetic energy because there's no more gravitational potential energy if we take the bottom of the hill as a zero height, which we can do. So we have a kinetic energy only, which will be the total mechanical energy. So what I'll do is I'll take this 450 and plug it in for the total mechanical energy. The 450 m is going to equal our 1/2 m times the velocity at point B squared. So what you see here, that m was concerning, but it's kind of nice here in this problem, the m cancels out. So we just multiply both sides by 2 and take the square root, and it turns out that the v at point B is 30 meters per second. So that's our answer to part A of this problem. All right, part B. At point C, the total mechanical energy at point C will be the kinetic energy at C plus the GPE at C. And once again, the total mechanical energy is still the 450. So we're going to have 450 m equals, not plus, equals the kinetic energy at C, which is 1/2 m times v at C squared plus m times 10 times 30. So we're going to have 450. Actually, let me cross this off first. Let me cross off the m's. The m's all cancel because all three terms have the m. That's the nice thing, once again. The m never really factored in here. So we're going to have the 450 equals 1/2 v at C squared plus 300. If you subtract the 300 from both sides, multiply by 2 and take the square root, you get the velocity at point C equals 17 meters per second. So we never even needed to know the mass. Example number 4, conservation of energy. We have a car that's going to start at rest from a hill 40 meters high. It's going to coast down, and because of friction, it's not going to make it as high on the second hill. So there's going to be some loss of energy, really not a loss, but a transfer to heat due to friction. But once again, I'm going to calculate the total mechanical energy at point A, which will be the GPE at point A. I'm going to do that off the grid here. Well, GPE at A, if I do the calculation, I'll do the M times G times H. You plug the numbers in that they've given you here. The GPE at A will be 452,000 joules if you plug in the mass and then 10 and then the height of 40 meters. The total mechanical energy at point B is also just GPE. The car came to a stop. And if I do the calculation there, the GPE at B comes out to be 339,000 joules. So there's a loss of energy. Where'd it go? Well, it went to heat because of friction. So there's quote-unquote loss. It's not really lost energy. But if I take the 452,000 minus the 339,000 joules, I get a transfer to heat of 113,000 joules of energy. And that's because of the frictional forces. Well, friction is doing work. The work done by friction is the force of friction times the distance you moved. And the work was this much. That's how much work friction does. It robs or transfers that energy into heat. So what we have here is 113,000 joules of work energy is due to the force of friction working against it over 400 meters times a cosine of 180 degrees, because friction is opposite the motion. End result here is you get F, the frictional force, is negative 280 newtons. And don't let the negative bother you. You could have just said the work was negative 113,000, and then the force of friction comes out to be a positive 280 newtons. But it's an average frictional force of 280 newtons against the motion.